Hi, in this video we are going to talk about the concrete implementation of the Splay tree. So first of all, we have to create a tree interface because it is a very good programming practice to program to an interface or a supertype. Basically, if you take a close look at how Java works, for example, linked lists, we can instantiate an array list as a list. List is equal to a new array list or a new linked list. So basically, this list is an interface in Java as well. So this is what we are going to do. We are going to program to a tree interface. So we have to create a tree interface, and because we would like to make it as generic as possible, because we would like to store integers, doubles, strings, and even custom objects in this tree, that's why we have to make it as generic as possible with the t parameter, which is going to extend the comparable interface. Okay, so we will have the methods such as the insert, the find, the get minimum, the get maximum, and the in-order traversal. We will have this node. Basically, this node is going to represent the nodes in the tree as usual. We are going to make it generic too, so that's why this T extends the comparable interface. Why is it important? Because we have to make sure that we will be able to compare nodes according to the parameter. So this T has to extend the comparable interface to be able to use the compare to method later on. So we have the data we would like to store, doubles, integers, custom objects, and so on, the right node, the left node, and we have to store the parent node. Okay, in the constructor it is going to get the data, and we set the data to be equal to this data. We have the get data, set data, the getters and setters for the nodes, the left node, the parent node, and the right node. And basically we have the toString method with the data.toString. Okay, what about the Splay tree itself? We are going to have several methods, but first of all we have to store a reference to the size of the tree. We have to store a reference to the root node, and because this Splay tree is going to be a tree, that's why first of all we would like to make it as generic as possible, and we would like to implement the tree interface with all the methods defined in this interface. Okay, so we have the root node. First we have the insert method, and basically we have a temporary node which is going to be initialized as the root node, and we have the parent node which is set to be null because in advance we don't know that what's going to be the parent node. And while the temp node is not equal to null, we basically have to search for the item we would like to insert. It is like the binary search tree. We have to find the location and the place where we want to insert the new data. So that's why we have to use this compare to method, and basically that's why we need this comparable interface to be able to use this compare to method. If it's smaller than this given data, then we go to the right. If it's greater, we go to the left. Basically, it's like the standard binary search tree. And if we are there, the location where we want to insert the data, then we instantiate this temporary node with the data, and we set the parent node accordingly. Okay, we have to check whether the parent node is equal to null, then the root node is going to be the temp node, because this is the first node we insert. Then we have to use this compare to method again to be able to set the right node and left node accordingly. And what's very important is this Splay method. We have been discussing in the theoretical section that after we insert the items, we have to splay it. What does it mean? That we have to make sure with the help of rotations that the newly inserted item is going to be the root node. Why? Because the Splay tree is usually the implementation of caches. So we would like to access in order 1 constant time complexity the recently searched items or recently inserted items. So that's why after every insertion we have to splay, and every search we have to splay. So after the find method, okay, it's not the search but the find whatever, we have to splay again. So whenever we insert new items or search for new items or search for items in display tree, we want to make sure that after the operation, it's going to be the item we were looking for and the node is going to be somewhere near the root node. Why? To be able to access it very fast the next time we are searching for it. Okay, so that's all about the insert method. Then we have the in-order traversal. If the root node is not null, then we are going to call this method, this in-order traversal. And this is the standard in-order traversal method as we have seen for binary search tree. We visit recursively the left subtree, then the root node, and then the right subtree. Of course, we have to check whether the left node is null or not, because if it's not a null, then we are going to traverse it in a recursive manner. Then we print out the actual root node. This root node is basically not just the root node of the whole tree, it can be the root node of the subtree as well, as we have discussed exactly for AVL trees and for binary search trees. And then we go to the right, so this is the in-order traversal. The getMin and the getMax is going to return the minimum item and the maximum item. If the null is not equal to null, we have to call this function. Why? Because if the root node is null, it means that our tree is empty. This getMin is going to go as far to the left as possible because the smallest item is the leftmost item. So if the getLeft node is not a null, then we are going to call this method recursively on the left node. And anyways, if the left node is a null, it means that this node is the leftmost node, so we just have to return with the data. The maximum is the same. We have to go to the right as far as possible because the maximum item is the rightmost item. So we get the maximum if the root node is not a null. If the root node is a null, it means that our tree is empty. It doesn't contain any items at all. And anyways, we are going to call this method recursively on the right node as far as the right node is not a null. If the right node of a given node is null, it means that this is the rightmost item. So we know that it's going to contain the data with the maximum value. So that's why we return with the node.getData. The print root is going to print the root as well, of course. The isEmpty is going to tell whether the tree is empty or not. So if the root node is equal to null, it means that it is empty. Anyways, it is not empty. The size is going to return the size. By the way, if we would like to make the code a bit fancier, I think that we can check whether when we get the minimum, for example, we check whether the root is not equal to null. So we can say that if the tree is not empty, like this. Okay, and it's going to work fine. And I'm going to do the same for the maximum. This root is not equal to null, it means that it is not empty. So just to avoid code redundancy, I'm going to use something like this. Okay, then the find operation is very similar to what we have seen, but instead of recursive method calls, we are going to use iteration this time. We have the temporary node, we initialize it to be the root node, and while the temp node is not equal to null, if the given data is smaller than the temp node's data, then we have to go to the right. If the temp node.getData compared to data is smaller than 0, then we have to go to the right. Else if the temp node.getData compared to data is greater than 0, it means that we have to go to the left. And else it means that they are equal. So we just have to splay the temp node and then we have to return with the temp node, because in every search operation we would like to make sure that the node we are looking for is going to be the root node, and this Splay method is going to make sure that it's going to be the root node. Anyways, we have to splay the tree, then we return with null. Okay, these rotate left and rotate right are exactly the same as we have discussed for the AVL tree, red-black tree, and so on. So I'm not going to talk about it. It is exactly the same. I've just copy and paste the code. And we have this Splay method. I'm going to talk a bit more about it in the next video. Thanks for watching.